Okay guys, so in the last class we were discussing skewness. In today's class we would be discussing kurtosis, and with kurtosis our discussion with respect to the shape of the distribution is going to be complete, right? So we had discussed that there are four moments that describe the shape of any distribution. The first moment was central tendency. And this central tendency basically told us where the returns of the distribution were centered at. What was the average return of any distribution? The second moment was variance, which basically addressed the risk of investing in a particular distribution. And we had basically said that, if the standard deviation of a distribution of stock returns is high, then that basically meant that that distribution had a lot of outliers, either positive or negative outliers. But this variance, this standard deviation does not tell me the location of the outliers. It does not tell me whether the outliers are positive or whether the outliers are negative. Now, what are your positive outliers? Positive outliers are extreme values which are significantly more than the other observations in a distribution, and a negative outlier is an extreme value which is significantly less than the other observations in a distribution. So variance, a high standard deviation, a high variance tells me that okay, the risk is high, but it does not, it tells me that there are extreme values in this distribution, but it does not tell me whether these extreme values are above the mean, that is positive, or below the mean, that is negative. So it's not telling me the location of the outliers. Then we have skewness. Skewness tells me the location of the outlier, right? So skewness, if a distribution is positively skewed or right skewed, then outliers are positive, right? Outliers are positive. That basically means that extreme values are above the mean. Extreme values are significantly greater than other observations in the distribution. And if outliers are negative, then we are going to have a negatively skewed or a left skewed distribution, right? And this basically tells me that the outliers are below the mean. They are significantly less than the other observations in the distribution. Okay. And last is kurtosis. Kurtosis is going to tell me the probability, or it's going to tell me the chance of an extreme event happening. So it's going to tell me what are the chances of an extreme event. What is the chance of an outlier occurring, right? So, so when we try to assess the risk of the distribution, we are not only going to look at HD. HD is going to be one part while you assess the risk of any distribution. You also have to look at skewness. You also have to look at kurtosis, right? So if a distribution is negatively skewed, then outliers are going to be below the mean, right? You are going to have negative extreme events, and if kurtosis is very high, then that would mean that the chances of this extreme event happening is very high. So negatively skewed distribution with a very high kurtosis is going to tell me that chances of extreme negative events happening is very high. So if you were to invest in such a distribution of stock returns, right? So if the distribution of stock returns is negatively skewed with high kurtosis, then the risk of investing in that particular stock is going to be very, very high, right? So that's what the idea is. Now we will discuss what kurtosis is. Okay, now before discussing kurtosis, I expect that you know what is a normal distribution. So please pardon me for my bad drawing, right? So this is, say, your normal distribution, right? And let us make a distribution with fat tails, right? So this distribution that I have drawn in blue has a fatter tail, right? So we all know that the mean is centered at the, mean is located, arithmetic mean is located at the center of the distribution, and your outliers are going to be in the tails, right? So your negative outliers are going to be here in the left tail, and your positive outliers are going to be here in the right tail, right? Okay. We know that your observations are on the x-axis, right? So this is your observations are on the x-axis, and the frequency with which these observations occur are going to be on the y-axis, right? So the frequency is going to be here. Okay. Now, frequency with which uh, outliers will occur in a normal distribution is going to be given by this particular area, right? Now, frequency with which outliers will occur in the normal distribution is given by this area. Remember, your normal distribution is this, drawn in this red line. So the frequency with which outliers will occur in this normal distribution is given by this yellow area, and frequency with which outliers will occur in this fat tail distribution, right, is given by this particular area, right? So you can notice that frequency with which outliers occur in this fat tail distribution is more than normal, right? uh, Basically, the chances with which extreme values will occur in this fat tail distribution is more than normal, right? It's more than normal by this much, right? This much. Okay. So in this fat tail distribution, chances of extreme value occurring are higher than normal, right? Remember, mean is at the center of a distribution, outliers are in the tails, positive outliers in the right tail, negative outliers in the left tail. Okay. Now notice this peak. See, in this fat tail distribution, observations closer to the mean occur with a higher frequency, right? So the peak of this fat tail distribution is more than your normal distribution, right? So this basically means that observations closer to the mean occur with a higher frequency in this fat tail distribution compared to your normal distribution, right? uh, right, and so there are more observations clustered around the mean in this particular fat tail distribution. And notice, guys, you know in this fat tail distribution, observations between the central region and the two tail region occur with a lower frequency, right? In this fat tail distribution, uh, observations between the central region and the two tail region occur with a lower frequency. So if you were to look at observations here and here in the fat tail distribution, those observations would occur with this much frequency. This would be the frequency with which observations would occur in this area. And in a normal distribution, you know observations would occur with a higher frequency in this area. Okay, so this is the broad idea, right? So the thing is that in this fat tail distribution, um, the chances of extreme values occurring is more than normal because of the fatter tails. Probability with which, or the frequency with which, extreme values will occur is more than normal. Extreme values are outliers, right? Okay. uh, Frequency with which observations will occur around the mean is also more than normal, right? um, Observations closer to the mean will occur with a higher frequency than your normal distribution, right? And in this factorial distributions, observation between the central region and the total region will occur with a lower frequency. That's what we saw here. Okay. Now this factorial distribution is known as your leptokurtic distribution. Right? It's called your leptokurtic distribution. Your normal distribution is also known as your mesokurtic distribution. Okay. Now let's understand this leptokurtic distribution. So, you know, in this leptokurtic distribution, chances of extreme positive or negative events occurring is more than normal, right? Chances of extreme positive or negative events occurring is more than normal. And see, if a distribution of returns of a particular stock is leptokurtic, then investment in that stock is going to be very, very risky, because the probability with which outliers, the probability with which extreme values will occur is higher in such a distribution. See, your outliers, your extreme values are the same thing, right? I've already told you that your normal distribution is a mesokurtic distribution, and we are comparing kurtosis with respect to how it differs from your normal distribution, right? So you know we are basically measuring how fatter or thinner the tails of our distribution are compared to the normal distribution. So your mesokurtic, your normal distribution is a kind of a benchmark against which we compare your kurtosis. Okay. Next you have a platykurtic distribution, which has tails thinner than your normal distribution. And in a platykurtic distribution, the probability or the chance of an extreme event occurring is less than your normal distribution. So extreme event again is an outlier. And notice I'm talking of both positive and negative extreme events, right? And if a distribution of returns of a particular stock is plateaukurtic, that basically means that the risk of investment in such a stock is very, very low. So it's going to look more or less like this. Your plateaukurtic distribution is going to look like this. So this is say your normal distribution. Then your plateaukurtic distribution is going to look like, it's going to be looking like this. So see, it has thinner tails than your normal distribution, right? It has thinner tails than your normal distribution. So here the probability of an extreme event occurring in a platykurtic distribution is this, and the probability of an extreme event occurring in a normal distribution is this. In platykurtic distribution is this. So here the probability or the chance of an extreme event occurring is less than normal in a platykurtic distribution. So this is your platykurtic distribution. Okay. Now we are going to calculate how you calculate kurtosis. So your sample kurtosis is given by this formula. S is basically your sample standard deviation. N is the number of observations in a distribution, and you sum up the you calculate the individual you calculate how much an observation deviates from the mean, and you raise the deviation to the power of, to calculate your numerator. What you are doing is you are taking an observation, then you calculate how much that observation differs from the arithmetic mean, how much it deviates from the arithmetic mean, and then you raise this deviation to the power of 4, right? So notice guys, the denominator and the numerator of this particular ratio is always going to be positive, right? So denominator is going to be positive because your n, which is the number of observations, is always going to be positive, right? And Your standard deviation, as we all know, is positive, right? And if I raise a positive number to the power of 4, it's still going to be positive. Okay. Now think of the numerator. Say the deviation around the arithmetic mean is negative. Now, when I raise this negative deviation to the power of 4, it's going to turn out to be a positive number, right? So if I raise all the deviations to the power of 4, all these deviations are going to be positive. So the sum of these deviations are going to be positive. So the numerator of this ratio is going to be positive. So both numerator and denominator are going to be positive. So kurtosis is never going to be a negative number. It's always going to be a positive number. This is something that we need to bear in mind. Okay. Now a mesokurtic distribution or a normal distribution has a kurtosis of 3, right? And a leptokurtic distribution is going to have a kurtosis of more than 3, and a platykurtic distribution is going to have a kurtosis of less than 3, right? So this is the broader idea. Okay, now many statistical packages report a measure called excess kurtosis, and excess kurtosis measure how much kurtosis of a distribution differs from a normal distribution, right? So how do you calculate excess kurtosis? Excess kurtosis is basically kurtosis of a distribution minus 3, where, and why are we deducting it with 3? Because normal distribution, a mesokurtic distribution, has a kurtosis of 3, and excess kurtosis is measuring how much the kurtosis of a distribution is differing from 3, how much is it differing from a normal distribution. So excess kurtosis of normal distribution is going to be 0. Why? Because kurtosis of a normal distribution is going to be 3, and while we calculate excess kurtosis, we deduct the kurtosis of a distribution from 3, no, by 3. So 3 minus 3 is 0, and your excess kurtosis of a leptokurtic distribution is more than 3, is going to be more than 0. Why? Because its kurtosis is more than 3. Leptokurtic distribution kurtosis is more than 3. So if I deduct any number which is more than 3 uh, with 3, then I'm going to get a positive number, right? So say if the leptokurtic distribution has a kurtosis of 4, then excess kurtosis is going to be 4 minus 3, that is 1. So if you see positive excess kurtosis in the examination, that basically means that the distribution is leptokurtic, and naturally excess kurtosis of platykurtic distribution is going to be less than 0. It's going to be negative. Why? Because a platykurtic distribution kurtosis is less than 3, right? So say it is 2, so excess kurtosis is going to be 2 minus 3, which is minus 1. So if in the examination you see that there is a distribution which has an excess kurtosis of minus 1 or a negative excess kurtosis, you have to understand that it is a platykurtic distribution, right? So kurtosis of a normal distribution 3, leptokurtic distribution more than 3, platykurtic distribution less than 3. But there is another measure, excess kurtosis, which basically measures how much the kurtosis of a distribution differs from a normal distribution, right? So if excess kurtosis is positive, then the distribution is leptokurtic. If it is 0, then the distribution is mesokurtic or normal distribution. And if it is platykurtic, if its excess kurtosis is negative, then the distribution is platykurtic. Okay, so that's about it, guys. Now see, guys, you need to, if the distribution of stock returns is negatively skewed and is leptokurtic, then investment in such a particular stock is very, very risky. Why? Because in a negatively skewed distribution, extreme values outliers are going to be below the mean. They are going to be significantly less than the other observations in the distribution. And if it is leptokurtic also, then these, the probability with which these negative extreme values will occur is going to be more than normal. So a negatively skewed distribution which is leptokurtic in nature is going to be very, very risky to invest in. This is something that you should bear in mind. Thank you guys. See you in the next video.